Hi, today I will be presenting ImCLR, Implicit Contrastive Learning for Image Classification. This is joint work with Samarth from University of Toronto and Anastasios Kyrilidis from Rice. So the first thing, what is the motivation for this work? Well, contrastive learning is an effective way for unsupervised representation learning. And while it's been applied to a variety of places, it's achieved the most attention and the best results recently in this area. The primary idea of contrastive learning is that you want to maximize the differences between images and minimize the differences between similar images. So this is typically implemented as a loss on the embedding layer, which encourages the cosine similarity between different augmentations of an input and decreases similarity between augmentations of different inputs. So for example, here I present the loss that is used in the ImCLR framework, and on the right here is MoCo. So there are some interesting questions out of this area. The majority of these works use a lot of compute and lie in this unsupervised representation learning. So there's some questions which are, can we decrease the amount of compute? What other areas can contrastive learning make a big difference? And the last question, which is the focus of this work, is do we really need that explicit loss? And can we actually do contrastive learning implicitly? So our idea is implicit contrastive learning, or ImCLR. And the way we induce implicit contrastive learning is through a clever construction. Namely, we add an additional a step in the augmentation pipeline, which is post-image augmentation and prior to the input. So as you can see here on the bottom, on the left, on this side is the standard one-hot image pipeline, which you may be familiar with for image classification. And on the right is the ImCLR pipeline. We simply add a step here where we actually take two or more post-augmentation images and concatenate them, while at the same time adding the average of their labels. And the motivation is that we want the network to actually be able to differentiate between, for example, in this example, which one is the frog and which one is the car, given that the network knows there is a frog and there is a car. And in this way, we want to induce implicit contrastive learning. I make a mention here that there is pretty much no change to pipeline, no change to loss, no change to hyperparameters, and no change to general network architecture. Our results are as follows. We get a good improvement in image classification, actually fairly significant in some areas. We also get improvements in terms of robustness against common permutations and augmentations. We also get improvements in the case of reduced samples. We also get improvements in the semi-supervised learning setting. And lastly, we show that we're actually complementary to existing image augmentations by combining ImCLR with CutMix or AutoAugment, which is state-of-the-art image augmentation methods, and we get generally improved performance.